Have you ever wondered how electricity works? In today's world where almost everyone is enjoying the convenience brought by electricity, sitting in aircon room, charging their computers and hand phone, but very few actually understand how it works. For this reason, today, we will introduce how electricity works in a simpler way. In the beginning, we will talk about the history of electricity, and some important scientist discovery that has led us to better understand the electricity. From there, we will reveal the main concept behind the electricity, that is the electric field and its characteristic. And lastly, we will discuss about the working principle of electricity and the importance of electric field as a source of energy in every circuit. Without further delay, let us start our discussion today. If you enjoy the content, please don't forget to hit the like button, subscribe to the channel, and turn on the notification bell so you never miss any update. The history of electricity. Back in the old days, ancient people did not have an understanding of electricity in the same way that we do today. The ancient Greeks discovered that rubbing fur on amber could attract lightweight objects like feathers. They also observed that lightning, but they did not fully understand the phenomenon. These observations were not understood at the time, however, they are examples in history of people observing static electricity and electric current. In fact, these two phenomena happened because of existence of electric field that we are going to discuss later. In 18th century, several key discoveries were made that helped to lay the foundation for our modern understanding of electricity. Benjamin Franklin conducted his famous kite experiment in 1752 to prove that lightning was a form of electricity. Franklin demonstrated that electricity was a single force that could be transferred from one body to another. He also coined several terms that are still used today, including positive and negative, to describe the charges of electricity. This experiment helped us to understand that electricity can be conducted from one point to the other, from the lightning, through the wet kite string, and down to the ground. Later in 1800, Alessandro Volta invented the first battery, known as the voltaic pile, which was made up of alternating copper and zinc discs separated by cardboard soaked in salt water. Alessandro Volta's invention of the first battery was a major breakthrough in the field of electricity. The voltaic pile creates an electric field that can continuously provide an electric current to a circuit. The unit of voltage or electrical potential, the volt, is also named in his honor. Overall, these phenomena and discovery of electricity has a fundamental concept behind, that is the electric field. An electric field is a space around a positively or negatively charged object, and is represented by electric field lines. But, when will an object become positively or negatively charged? In an atom, protons have a positive charge and electrons have a negative charge. Normally, the number of protons and electrons in an atom is equal, so the atom is neutral. However, if an atom loses or gains electrons, it becomes positively or negatively charged. Let's recall that the ancient Greeks discovered that rubbing fur on amber could attract lightweight objects like feathers. When fur is rubbed against amber, electrons are transferred from the amber to the fur due to frictional force, and amber becomes positively charged that can attract feathers. Moving on, for a positively charged object, the electric field lines radiate outward from the object in all directions. Whereas for a negatively charged object, the electric field lines point inward toward the object. These invisible lines indicate the direction and strength of the field. When two charges are placed together, their electric field lines will be distorted due to the interaction. This interaction generates a force called electrostatic force. For example, the like charges, such as the positive and positive, or negative and negative charges, repel each other because their electric field lines bulge outward between the two charges, indicating the direction in which the electric field is pushing each other. Whereas for opposite charges, such as positive and negative charges, the electric field lines will be compressed between the two charges, indicating the direction in which the electric field is pulling. Therefore, the opposite charges will attract each other. An easier way to remember is taking magnets as example. When we try to bring like poles of two magnets, such as the north and north, or south and south, near to each other, we will experience a repulsive force. If we bring opposite poles, such as North Pole and South Pole together, the magnets will stick together immediately. The electric field is closely related to our everyday life, but electrical appliances normally use voltage as the rating. However, electric field and voltage can be related by the Coulomb's law of charge. With greater electric field between 2 points, the higher the voltage will be. For example, the battery that we normally used in a remote control has 1.5 volts between its positive and negative terminals. The handphone is charged with 5 volts adapter. Our car battery is around 12 volts. Laptop is charged using 19 volts adapter. And electric plug in our home is having 120 volts or 220 to 230 volts. In our natural surroundings, before lightning occurs, one of the strongest electric field in millions of volts is built up between the lower part of the cloud and the ground. When the electric field becomes strong enough, it creates a powerful electrical current flow followed by a bright flash of light and a loud thunderclap. After understanding what electric field is, let us take a deeper look at the working principle of electricity, to further understand the importance of electric field and its application. Taking the following circuit as example. A battery has an electric field across its positive and negative terminal. However, this electric field will not be useful until a complete path is formed. When a battery is applied across the conductor, it creates an electric field across the circuit. Due to the electrostatic forces, the negative charges on the negative terminal of battery repel the free electrons in the wire. This creates a net force on the electrons across the circuit, continuously pushing them towards the positive terminal of the battery. While the electrons are moving, they will collide with the atoms of conductor and filament of light bulb, transferring their kinetic energy into the form of heat energy. As a result, the electrons slow down. The electric field of battery acts as source of energy that constantly push the electrons. The electrons then gain energy to move, and collide again with atoms. The process of gaining energy from electric field and losing energy due to collision keep repeating. Heat built up at the filament, and eventually the bulb emits light. One may think that electrons must be completing the loop very fast from negative to positive terminal so that the bulb will light up. However, that is not correct. Electrons is drifting very slowly from one place to another because they are constantly colliding with atoms. It is important to note that electrons do not physically move in the traditional sense of a straight line through the wire like water flows through a pipe or ball rolling down a tube, that is without any obstacles blocking them. Instead, the movement of electrons is an intermittent flow because of large atoms blocking the path. For easier understanding, let's look at the following illustration on how electrons flow in a circuit. They are constantly colliding with the atoms in the wire, transferring some of their kinetic energy to the next atoms. This causes the electrons to lose some of their energy, and as a result, their speed slows down. Due to the electric field constantly providing the energy to electrons, the electrons then gain kinetic energy to move and collides again with atoms. The process repeats, and the average net movement of electrons in a specific direction is what we called electric current. How fast do you think electrons move in a circuit? The drift velocity of electrons is very slow in wire as they collide with atoms, transferring their energy, and slows down. For example, the drift velocity of electrons if 2.5 mm square copper cable is used, and for current of 1 ampere, the drift velocity is around 10 cm per hour. Taking the previous circuit as example, if a 1.5 volts and 0.3 amperes light bulb and 2.5 mm square copper cable with total length of 30 cm are used, the average drift velocity of electrons will be approximated as 3 cm per hour. In order for a single electron to complete the journey from negative to positive terminals, it requires up to approximately 10 hours. That's extremely slow. But you may wonder why the lamp lights out immediately when we switch it on. It is the electric field that builds up and propagates along wires at essentially approximate the speed of light. Subsequently, the electrons across every part of the circuit are simultaneously being pushed from negative terminals towards the direction of positive terminals. At the filament, the enormous number of collisions between electrons and filament atoms build up heat energy quickly and the bulb lights up. The whole process may take many stages, however it happens in approximately the blink of an eye. This explains why the bulb can light up immediately when we switch it on. The simple electric circuit explains how electricity works and is fundamental to all electrical systems nowadays. In our modern electrical grid system, electricity generated at power plant is transmitted over long distances to reach our homes, and then distributes to individual circuits. From there, the electricity is used to power our lights, appliances, and other electrical devices. Overall, the electric field is responsible for transferring the electrical energy from the generating station to transformer substation, and into our homes, almost instantaneously. Looking back at the history, thanks to the ancient people and scientists who discovered the fundamental principles that help us harness electricity today. Without their curiosity, innovation, and hard work, we would not have the electrical power that we rely on so heavily in our modern lives. In summary, we learn about electric field as a continuous source of energy in every circuit that keep the electrons flow. Besides, the electrons across every part of the circuit are being pushed simultaneously when electric field is applied, and they flow very slowly in the circuit as they collide with atoms. Last but not least, even though the electrons drift very slowly, they are a large army that collides with atoms, transferring their energy gained from electric field, and bulb lights up almost instantaneously. That is it for today's topic on how electricity works. Please like, subscribe and turn on the notification of our channel. We will constantly update more topic covering electrical knowledge in future.